Let A be any 2 by 2 square matrix. From our previous knowledge, the determinant of A can be evaluated, which is quite simple. However, evaluating the determinant of a third-order square matrix is a bit complex and a lengthy process, as there are so many terms to be multiplied and then simplified. However, by using some properties of determinants, we can obtain the maximum number of zeros in a row or a column in a determinant which simplifies the evaluation. Let us learn these properties one by one. The first property is the determinant of a matrix is equal to the determinant of the matrix obtained by interchanging its rows and columns. In other words, the value of a determinant remains unchanged if its rows and columns are interchanged. Let A be 3 by 3 square matrix. Let's evaluate the determinant of A. By expanding it along the first row, we get A1 times of B2 C3 minus B3 C2 minus A2 times of B1 C3 minus B3 C1 plus A3 times of B1 C2 minus B2 C1. Now, let B be the matrix obtained by interchanging the rows and columns of matrix A. To verify the property, we have to show that on expanding determinant B along any row or column, we get the same value as we get on expanding determinant A. So, let's expand determinant B along the first column. Observe that we get the same value as we get on expanding determinant A. Hence, we have determinant of A is equal to determinant of B, and matrix B is nothing but transpose of matrix A. Thus, the determinant of square matrix A is equal to the determinant of its transpose. Let's consider an example to verify the property. Let A be a 3 by 3 square matrix as shown. On evaluating determinant A along the first row, we get it equal to -1. Now, A transpose can be obtained by interchanging the rows and columns of matrix A. Evaluating determinant of A transpose along the first column, we get its value equal to -1, which is the value of determinant A. Hence, the determinant of matrix A is equal to the determinant of its transpose. In a determinant, the ith row is denoted by R with subscript I. Similarly, the ith column is denoted by C with subscript I. Mathematically, an interchange of the rows and columns in a matrix is denoted as shown. Let's now move on to the next property. It says that the sign of the determinant of a square matrix changes if any two rows or columns in the matrix are interchanged. Consider a 3 by 3 square matrix A. Let's evaluate the determinant of matrix A. By expanding it along the first row, we get A1 times of B2C3 minus B3C2 minus A2 times of B1C3 minus B3C1 plus A3 times of B1C2 minus B2C1. Now, let B be the matrix obtained by interchanging the first two rows of matrix A. To verify the property, we have to show that the determinant of matrix B is the negative of the determinant of matrix A. So, let's expand determinant B along the second row. We get minus of A1 times of B2C3 minus B3C2 plus A2 times of B1C3 minus B3C1 minus of A3 times of B1C2 minus B2C1. Observe that this is the expansion of the minus of determinant A. Thus, we have determinant of B is equal to minus of determinant of A. Hence, we can say that a determinant changes its sign when two rows or columns are interchanged. This verifies the property. Let us now verify it by taking an example. Let A be a 3 by 3 square matrix as shown. On evaluating determinant A along the first row, we get its value equal to minus 1. Let B be the matrix obtained on interchanging rows R1 and R2 of matrix A. On evaluating determinant B along the first row, we get 1, which is equal to minus of determinant A. Hence, the determinant of matrix B is equal to the minus of the determinant of matrix A. Moving on to the next property. It says that if any two rows or columns of a square matrix are identical, then the value of its determinant is 0. Let us consider a matrix A, in which the elements of the first row and the second row are identical. Expanding the determinant of matrix A along the first row, we get A1 times of A2 B3 minus A3 B2 minus A2 times of A1 B3 minus A3 B1 plus A3 times of A1 B2 minus A2 B1. On simplifying, we get the determinant of matrix A is equal to 0. Similarly, the determinant of matrix A is 0 if any two columns are equal. Hence, if any two rows or columns of a square matrix are identical, its determinant is 0. Let us now verify it by taking an example. Let A be a 3 by 3 square matrix such that its first and second columns are the same. On evaluating determinant A along the first row, we get zero. Hence, the determinant of a matrix, when two of its rows or columns are identical, is 0. This verifies the result.